let me tell you the analog in the 2D. In 1D, the model family is provided by the family of quadratic polynomials. In 2D, the family that I want you to keep in mind is something called the Renorm family, which is given by maps of the form. So it's a two-parameter family, being in dimension 2. And the first coordinate is given by something that looks like quadratic polynomials, x squared plus a minus by. Yes, this looks like a quadratic polynomial, but then there's this extra term involving y, and the second coordinate is just x. And then the parameter a and b can be chosen from the roots, like so. So since this is a two-parameter family, it can be visualized by a plane. The Renorm family is isomorphic to the plane. Let me put as the horizontal axis different values of A, and the vertical axis different values of B. Right? A very simple computation will show that if you have a map of this form, then the Jacobian is identically equal to the second parameter B. Okay, so the second parameter tells you the Jacobian of your map. So in particular, if you're on the upper half plane, these consist of Renorm maps which are orientation preserving because it has positive Jacobian. Here, orientation reversing. If you look on the line b is equal to 1, then these are all area preserving Renorm maps. If you go above, b is greater than 1, it's area expanding. Here, area contracting, or we call it dissipative. Yeah? And if you look at the line, the a-axis, which is the line when b is equal to 0, then you have a one-parameter family of degenerate Renorm maps, which can be identified with actually the quadratic family. Right? So this can be identified with the quadratic family because if you let b is equal to 0, and you look at this map, well, when you let b equal to 0, you just have this. Right? And when you iterate this, it's the same thing as just iterating the first coordinate, and you can ignore what happens to the second coordinate. So on this line, we have a family of maps that we're used to from 1D, and you can think of the Renorm family as a two-dimensional extension of this one-dimensional family. Okay? Right, so for the quadratic polynomials, its dynamics is now completely understood thanks to the fact that we have this nice renormalization theory. But for the Renorm family, well, the dynamics is still quite wide open. And the goal of myself and my co-authors was to try and take the renormalization theory that has worked so well in 1D and try to generalize it to 2D. Okay, so that is the underlying goal. So this is the family that I kind of want you to keep in mind. Okay, throughout this talk. All right, so the key difficulty in higher dimension is just to define what it means for the map to be unimodal. Okay, so in 1D it was trivial because it's unimodal if it has a unique critical point, and the critical point is where the derivative is equal to 0. Right? If you try to do something similar for this family, you'll quickly run into trouble because it's a diffeomorphism, this Renorm maps. The Jacobian is constant. Right? So if you require the critical point is where the derivative vanishes, well, the derivative never vanishes, so there would be no critical point. Okay? So actually, it will take us, I think, most of the time we have left to just define what it means for a diffeomorphism to be unimodal, and then we'll be able to, but once we identify what this is, we'll be able to develop a renormalization theory, which is analogous to what we have in 1D, for 1D unimodal maps. Okay? All right, so good. But before we get to unimodality, it's much easier to define what it means for a surface diffeomorphism to be renormalizable. So let's start with that. So the class of maps that we're interested in 2D will act on the 2D analog of an interval, which will be a Jordan disk. So let omega, which is a subset of the plane, be Jordan disk. And by Jordan disk, I mean something that looks like, okay, I'll draw it here. Something that looks like this. So it's a topological disk, and the boundary is a topological circle. Okay, so topologically it's a very tame object, but the problem is that the geometry could be arbitrarily bad. Yeah, so here's one important difference between 1D and 2D. In 1D, the domains were integrals, which have very simple geometry, but in 2D, that's not so much. Okay, so then we'll look at a map which takes this disk compactly into itself. And we'll assume that it's C2, just like in the 1D case. C2, diffeo. And we'll assume that this map F takes this disk and maps it compactly into itself. Like this. F. And we'll assume it's C2, and we'll also assume that it is dissipative. So area conjoint. Okay. Actually, we need to assume something stronger than just dissipation. We need to assume something called proper dissipation, which for now, let me not define. I'll define it later when we need it. Okay. But just know that in the Renorm family, you can guarantee proper dissipation if you require that the Jacobian is less than 1/4. Okay, so it's something which is not hard to guarantee, although it is kind of restrictive on what kind of maps you can talk about. Okay, so it's C2 diffeo and it's properly dissipative. So you have this Jordan disk, which is mapped compactly into itself by this diffeomorphism. Then we would say that this map is renormalizable. Definition. F is renormalizable if, just like in the 1D case, you have a periodic part of your domain is periodic, with period greater than 2, greater than or equal to 2. If there exists some r bigger or equal to 2 periodic Jordan subdomain let me call it D, compactly contained in your original domain. So there should be a part of this domain, let me draw it like this, which is also Jordan disk, I call it D, right? And when you act on it by your map, it jumps around in your space for some finite amount of time, and meanwhile it should stay disjoint from where it originally came from, but then after you iterate r times, it has to go back and map compactly into itself. So you map it once, it goes somewhere here, let's say. You map it again, it goes here. But then you map it r times, and it should take this subdisk and map it compactly into itself. Okay, so again, we have the self-similarity of a Jordan disk being mapped compactly into itself by a C2 dissipative diffeomorphism. Okay, then we would say that it is renormalizable. And again, we can define the first return map. First return map as PR of F, which is just the return map to this domain. Like this. Okay, and if we want to avoid the sizes of the domain getting too small, we want to rescale it so that it is of some standard size. Here, let me be vague. Here, it's actually not enough to just make it affine. Okay? But we'll talk about this later. Okay? So there's some rescaling. It's not so bad. Okay? But it's something close to affine. It can't exactly be affine, so it's not linear rescaling, but it just has to be quadratic rescaling. But we'll talk about this later. So we rescale this in some way to obtain the renormalization, which is given by, well, the same notation, script R of F. Okay, so we get this diffeo acting on a different domain. And like before, we're interested in the case where you have this self-similarity occurring at infinitely deep scales, right? So we will suppose that f is infinitely renormalizable, so that for all n bigger or equal to 1, there exists some Rn periodic Jordan domain Dn compactly contained in the previous Jordan domain, which is compactly contained in the domain of your original map. So what we have is some sequence of periodic domains. So this was the first one, D1, and inside we have some subdomain, which I'll call D2. And under the return map, the first return map, it should go somewhere inside, but away from where it started from. And then if you iterate enough, it should come back and not compactly renormalizable. Okay, and this repeats at infinitely deep scales.
Excuse me?
Yes?
In the one-dimensional case, you require that the return is unimodal. That if you start with some class of map, and you say, oh yes, I want that the return belong to the same class of map.
Right.
And here you don't seem to require any...
Yeah, because so far our class of maps is just C2 diffeo dissipative on a Jordan disk. Right? Yeah, so there's no unimodality to try and preserve under renormalization. That's something that we will define later on, and by definition it'll be kind of preserved under renormalization. But for now, let's not worry about it. Okay, for now, just we have diffeo. Okay, so we have this infinite nest of domains, which again we can spread around by the dynamic. So if we have this deeper level periodic domains, you iterate by your original map, to spread it around. And since you have infinite nests of these periodic domains, you can take the union and then take the nested intersection to get some kind of Cantor-like set floating in two-dimensional space now. So we form the odometer, which we call lambda, and this, you take the cycle of your nth renormalization domain to Rn minus 1, and then you take the nested intersection as n go to infinity. Okay, so this is a topological attractor. It's totally invariant, it's compact.
Is it combinatorial or what do we know?
A priori, we don't know. Yeah, a priori, we don't know that it's totally disconnected. Okay? Yes. So it's something that has the structure of an adding machine, structure of a Cantor set, but we don't know if all the connected components are trivial, because for that we would need to know something about the geometry of these domains, right? Well, in particular, in order to guarantee that all the connected components of this limit set, so when you take the nested intersection of all these cycles, we get this kind of compact, very disconnected set. But in order to be Cantor, each connected component would have to be a singleton. But to guarantee that it's a singleton, you have to make sure that every sequence of deeper and deeper renormalization domain containing that point the diameter has to go to 0, right? Which is some kind of geometric condition which there's no way to guarantee in this kind of general case, right? The only thing that we assumed was a topological kind of picture, right? There's no way to conclude that anything happens with the geometry of these maps. Oh, I don't know. I mean, that's that in 2D or in 1D? In 1D, yeah, that's right. Yeah, that's right. Yes, but the hope would be that if you assume that the combinatorics is nice, that if it's holomorphic, then it just follows.
No, for quadratic polynomials. Combinatorics.
Yeah, bounded type combinatorics. Yeah. So that would be the hope, but we're not quite there yet. Yeah? Okay, so we have this odometer, and again, since it's infinitely renormalizable, we can look at deeper and deeper first return maps. So we have the nth first return, which is given by P R of F and it's the first return to the nth renormalization domain like this. And then, there's this rescaling map, which I'm being vague about. I'll be less vague, hopefully, later on. So we have this n first return, rescale, and then we obtain the renormalization. Rf. Right, so you can kind of think of this rescaling as taking the smaller domain, and, well, at least a component of this rescaling will be something affine, which blows up the size, so that it has some unit, well, at least unit size. Okay, so that you don't just have, in the limit, get a map which is defined on a single point. Yeah? Okay, so like before, to understand the dynamics of the original map, we want to understand what happens to the sequence of deeper and deeper renormalizations. Okay, so the question is, what happens to this? As n go to infinity, what happens to the sequence of renormalizations? And one preliminary basic observation that you can make is that the more you renormalize, the more you zoom in this dynamics, the more one-dimensional the picture becomes. Okay? And the reason is because, well, how do you get the renormalization? You have to take big iterates of your dissipative map, right, which is area contracting. So the more you apply this map, the more area contracting it becomes. So in other words, the Jacobian of your renormalization goes to 0. Right? So you can kind of think of it as, in this example, when your Jacobian goes to 0, you crash down to the a-axis where you can identify with a one-dimensional system. Okay, so in this sense, the more you renormalize, the more you become one-dimensional. But at the moment, that's kind of all you can say about this class of infinitely renormalizable diffeomorphisms. Any questions about this? Okay. So observation. The more, well, let me write it this way. R and F becomes more 1D, whatever that is. Okay? And in fact, if you were to take any kind of meaningful limit of the sequence of renormalizations, then it should be some degenerate 2D map, which you can easily identify with just the 1D dynamical system, right? So for example, something like this, if you can take some kind of limit. Yeah. All right, good. And let me state the main results that we want to talk about. Yes? Yeah, so the rescaling is not as easy as in 1D. So in 1D, you can just do affine rescaling to make it some fixed length. In 2D, you need to first apply some fixed nonlinear transformation, and then do an affine rescaling. But I'll talk about that hopefully before the end of this lecture. Okay, so just hold on. All right, so this is the main results. A priori bounds in 2D. So this is the results that I did with my co-authors, Sylvain Crevizier, Misha Lubitsch, Enrique Pujals, and myself. Okay. And the statement is as follows. Okay. So I haven't defined one of the hypotheses. In fact, I haven't defined two of the hypotheses because I haven't defined what properly dissipative means. But let's assume that we have a diffeomorphism, infinitely renormalizable and properly dissipative. Okay? If we further assume that it's unimodal, in the sense that I'll define right after, if F is unimodal on this renormalization limit set, whatever this means, then we have the same result as in 1D. Then the sequence of renormalizations is pre-compact. Okay, so if you zoom in into this dynamics, you don't have, the picture doesn't degenerate into something wild. Okay, so it's something tame. You can take subsequence in order to get something convergent. And actually, you can say moreover, any limit of a subsequence of the sequence of renormalizations will be a 1D unimodal interval map. Will be 1D unimodal interval map, which we discussed. Yeah?
Why are you calling them a priori bounds?
Oh, that's a good question. Okay, so it's a term which everyone claims that Sullivan came up with, except Sullivan himself, apparently. So he got it, I mean, if he got it, from PDEs. So in the field of PDEs, apparently there's something that you, a priori bounds is something that you start with before you try to analyze, before you try to guarantee the existence of a solution. So it's some kind of control on your system just based on what you know about it before you try to guarantee existence of a solution and other nice properties. Okay, so I think that's where I got it. Yes. Although I've been told that in PDEs, a priori bounds is very easy to get, whereas in dynamical systems, it's very hard to get. Okay, so this is pretty compact. Any limit will be a one-dimensional unimodal map, and actually,
Question?
yes.
So for that, C2 smoothness is sufficient?
Yeah, C2 smoothness is sufficient. Maybe we can even get away with something less than C2. Definitely we need C1 plus alpha because we need to use Poisson theory. And we probably need something like bounded variation something. Yeah. But C2 is simple and it's sufficient.
And for the limit unimodal map, what kind of smoothness you can guarantee?
Oh, that's, okay. Let's say C2, although if you assume some additional things, then you can guarantee that it's analytic. Yeah.
Excuse me also.
Yes.
When you say any limit will be unimodal,
yeah.
You can choose the return so that, or you know that each time you have some return and you take limit, it will be like that.
So as long as you have, so if you take a converging subsequence, the limit will be unimodal.
Anyone
will be unimodal, yes.
Sure?
Yeah. Yes. But if it has to be unimodal. It has to be unimodal. Okay, so then what else is there? It's also, okay, the converse is also true. Moreover, okay, if you didn't like this, then you're gonna really hate this. A stronger version of the converse is true. Version of converse is true. So if you can find, so stronger version of the converse means that if you can find some subsequence of this, which converges to a 1D unimodal interval map, then you can guarantee that actually the map has to be unimodal, in the sense that I still haven't defined, but yeah. Okay. All right. There's a question? Sorry, I have a hard time hearing. So could you repeat your question, sorry? Oh, are you talking about some kind of universality in the sense that we can get any 1D unimodal map as a limit? Was that the question? No? Sorry, I
Maybe
can't
he's
see.
asking about embedding
Yeah.
one-dimensional maps.
Oh, yeah. That's right. Yes. I mean, if that is the question, exactly. So you can embed it in very similar way to the way we embedded the quadratic polynomials into two-dimensional maps. To basically, well, I mean, you can embed it whichever you want. I guess the more common one back in the day was if you had a one-dimensional map like this, then you would embed it into the space of two-dimensional map by making it like this, f of x, and then just 0 as a second coordinate. I think for at least unimodal maps, it's better to embed it like this. But some kind of degenerate embedding like this will place your one-dimensional system trivially into two-dimensional systems. Yes. And actually, this was how the previous work on renormalization was done. Was to embed the 1D family into the space of 2D families, and then use the fact that the renormalization operator is hyperbolic to try and get information about nearby 2D maps. I don't know if that was your question, but Oh, yes, yes, you can, yeah. Well, it depends on kind of what you mean. So it will kind of depend on the. Yes, you can, although I don't think it will be kind of a one-to-one correspondence, and I also don't think it will be kind of meaningful to require a one-to-one correspondence. Yeah. Okay. I see. Okay. So for now, actually, you know what? You remind me. I keep forgetting to do this. So this theorem, I stated it too generally. This actually is only for bounded type. So combinatorial should be bounded. Then yes, I believe so. Then yes. So by combinatorics is bounded, what I mean is, so each time you renormalize, you get a higher and higher period, right? So combinatorics bounded means that the relative period, as you go from one renormalization level to the next, should have some uniform upper bound, okay? So it should be at most, let's say, 1,000,000 times the previous period, okay? But that should be a hard cutoff. Sorry, I forgot to. I don't know if, does that make it more believable that you have this result? Yeah. Okay. Yeah. Okay. Thank you. Although, I mean, this doesn't mean that it's not true in unbounded case. It's just no one has worked on it yet. Okay. All right. So now I think I should try to define what unimodality means. If it's okay. Yes. You have a
So, what do you mean by one-dimensional unimodal interval map?
Yeah.
So, I suppose that's.
So what I mean is, okay, so this has to do with the kind of rescaling that I talked about before. So you can rescale this map, so you can do some kind of coordinate change, so that the map becomes something of the form. It's a 2D map, and it will become something of the form fn of x minus something that depends on x and y, comma x.
I see.
And this will be unimodal, and this thing will go to 0 very, very fast. Okay, so this is why you can't just do affine rescaling, because if you just did affine rescaling, I mean, there's no way that you'll get exactly this form, right, for the map. Yeah? Okay. All right. So now let's try to. Okay, how much time do I have? What do you think?
Till around 11, so about 25 minutes.
25 minutes? Okay, good. All right, so let me define unimodality, and then we'll wrap up today's lecture. Okay. So in order to define unimodality, we really have to, so like I said, in 1D, the geometries of the domains is trivial, right? Because they're all intervals. So there's no geometry to speak of. But in 2D, we have just these random topological disks, and the geometry could be wild. So we need to, before we can go further, we need to try and analyze what this picture could look like under the assumption of infinite renormalizability. Yeah? So here are some preliminary facts, which are not trivial. They require proof, but we'll just take as given. So proposition. If you look at this renormalization limit set, this odometer that you get by taking the nested intersection, then fact one, it is uniquely ergodic. So F restricted to this limit set is uniquely ergodic. Ergodic. So it is unique invariant measure, probability measure mu. So let me call the invariant measure mu. Just write it there, okay? And with respect to this unique invariant measure, the Lyapunov exponents of your map, there has to be two because it's a two-dimensional system. Lyapunov exponents are, and these Lyapunov exponents, one of them has to be neutral. One of them has to be zero. Zero. And then the other one has to be negative because it's a dissipative map, so there has to be contraction, right? So if one direction is neutral, the contraction has to come from the other direction. And this negative number I'm going to call log lambda. How familiar are we with Lyapunov exponents? It came up in the other mini course, but I guess this is a more geometric kind of perspective on Lyapunov exponents. Okay, so basically the fact that we have one neutral Lyapunov exponent and one negative Lyapunov exponent means the following thing, has the following consequence on this two-dimensional dynamical system. So basically, if you pick a typical point with respect to this measure, then it has the property, so let's say that's a typical point P, then it should have two invariant manifolds, which intersect at this point. There's a stable manifold, which I'm going to call WS of P, right? Which corresponds to the negative Lyapunov exponent. So this is the curve along which you see the contraction coming from the negative Lyapunov exponent. And then there is another manifold, which I'll call WC of P, and that is the center manifold, and that corresponds to the zero Lyapunov exponent. Okay? And to understand the geometry of this two-dimensional system, well, at least to me, it seems that it's equivalent to try and understand the geometry of these curves that you have for typical points. Okay? And to do this, we need to employ a very classical theory due to Pessin.
Sorry, why is one neutral?
Why is one neutral? Well, okay, so this is not trivial, but intuitively, sort of hand-wavy way, what you can think of is that on the odometer, it can't be hyperbolic. So there can't be exponential expansion or contraction on the odometer. So if for a typical point, if you point in the direction of the odometer, then you should see neither expansion nor contraction. Okay, so that's why one of them has to be zero. Yeah, it's kind of.
The paper was labeled for one-dimensional complex.
Yeah.
With unbounded geometry, and under some assumptions we can prove measure has exponent zero, but it's different.
Yes, there it's even better because there you prove it also for critical point, the critical ordinate, which is actually like an inspiration for our work.
But then it follows about
the
result is about invariant measures.
Right. Okay, so we have this stable and center manifold, and to try and understand their geometry, we're going to employ Pessin theory, which will tell us the following. Okay, so it will tell us that if you pick any epsilon, really small, positive, yeah, then for almost every point let me call it P naught inside the odometer. There exists some constant L, which depends on this epsilon and the point. So L depends on epsilon and the point, and this is bigger or equal to 1, such that, okay, I'm going to write something down, and then I'm going to define what I wrote using a picture, okay? Such that P naught is L epsilon Poisson regular. So this is what Poisson theorem is, okay? The fact that you have these Lyapunov exponents means that for a typical point, you have stable manifold and you have center manifold. But actually, we can say a lot more about what they look like, at least locally, near the points themselves. So, what is the picture? The picture is this. So let's say you have a typical point, and let's look at its orbit, forward and backward orbit. So this is P naught, P1, P2, and so on. And this is P minus 1, P minus 2, and so on. So this is a typical point. So if it's a typical point, then it has to have a stable direction, which is the tangent vector to the stable manifold, and a center direction, which is tangent to the center manifold. So let's say it looks something like this. So I'm going to call the stable direction ES, and the center direction EC. Okay. And in fact, this is the definition of Lyapunov exponent. Well, no, but okay. But as a consequence of the fact that these are the Lyapunov exponents, it means that if you look at the average growth rate of the derivative of your map, of your dynamics, along the stable direction, the average exponential growth rate should match this exponent, lambda. Okay? By the way, lambda is a number between 1 and 0. So the fact that you have this stable direction means that if you iterate forward and you look along this direction, you should have, on average, an exponential contraction by factor lambda, right? And if you go backwards, then you should have exponential expansion by factor lambda. Well, by factor lambda over 1. And the center direction is something similar. On average, if you look at the growth rate along this direction, on average, it should be something like 1. E to the 0, which is 1. Okay? So this is the setup that we have, but actually we can say a lot more. So let's spread this direction, the stable and center direction, by the dynamics. So you map it forward, and then you will get a bunch of directions corresponding to the stable and center direction, like this. Okay. And the fact that this point is L epsilon Poisson regular tells you that the local dynamics of your map near this orbit can be linearized in an epsilon shrinking neighborhood of size 1 over L. So let me draw what that means. So what you can do is you can cover this orbit by balls. Okay? And the sizes of these balls, you'll start with the biggest ball in the middle, and this will be of size 1 over L, to reflect the fact that this thing is L Poisson regular. Yeah? But then as you go forward, you have control. So these balls tells you where you have the control of the geometry. And as you move away from your center point, the amount of control, you lose the amount of control exponentially fast, but slow exponentially fast. So namely, as you go forward, the radius of these balls shrinks exponentially, but only by some epsilon factor. So this one will have the same radius as before, 1 over L, but since you moved one step forward, you have to contract it by a factor of lambda to the epsilon. Okay? So lambda is something less than 1, so if you raise it to some very small power epsilon, it will be something really close to 1, but still slightly smaller. Right? So it's a slight shrinking of your initial ball, which was of size 1 over L. Okay? And you have to keep doing this every time you move. So here it will be 1 over L 2 epsilon. Here, it will be 1 over L lambda to the epsilon. Here, 1 over L lambda to the 2 epsilon, and so on.
And sorry, inside each of these balls, what control do you have?
Well, okay, so I'm about to draw it. Yeah, but that's where you control the geometry. Okay. Of what? Okay, very good question. So you have this dynamics, which sends at least a center point to the next center point, right? By this nonlinear map. But what Poisson theory allows you to do is to have a say in how this picture transforms as you go from one to the next, right? But as long as you restrict yourself to just these balls, okay? So what you can say is that on each of these balls, there is a change of coordinates, which I'm going to call phi by the index, so phi minus 2, phi minus 1, phi 0, phi 1, phi 2, and so on. So that will send these balls downstairs. And these changes of coordinates will have the following properties. First of all, it will send the orbit points to the origin. It will send the stable direction to the vertical direction. The center direction to the horizontal direction. And if you were to factor the dynamics through this change of coordinates, then your dynamics become the simplest thing that you can have, right? With the requirement that along the stable direction you have contraction by lambda, and along the center direction you have, well, no contraction or expansion. Namely, the map, if you factor through here, the map going from here to there, downstairs, you can pretend that it's just a linear map given by this diagonal matrix 1, 0, 0, lambda. So along the stable direction, nothing happens, or along the center direction, nothing happens, along the horizontal direction. But along the vertical direction, you have this exponential contraction by lambda. So you have this at all steps. 1, 0, 0, lambda. 1, 0, 0, lambda. 1, 0, 0, lambda.
How far from identity are these changes of coordinates?
Very good question. So, well, identity is not quite the right thing to compare it to, but what you can say is that the CR norm is controlled, or C2 norm of these things are controlled. So if you look at the mth change of coordinates, and you look at the C2 norm, it will be bounded by L times lambda to the minus epsilon absolute value. So as you go further and further, the quality of these changes of coordinates will grow exponentially, but slow exponentially. Yeah, so this is what allows you to gain control of this system. All right, and I mentioned that this will allow you to control the geometry of the stable and center manifolds. This is because downstairs, the stable and center manifolds are just given by vertical axis and horizontal axis. Right? So that means that upstairs, the actual stable and center manifold, you just get by pulling these straight lines by the changes of coordinates. Right? So upstairs, if you look at the piece of the stable manifold which intersects this ball, where you have control, it will be some C2 curve whose C2 norm is bounded by the C2 norm of the change of coordinates. Right?
Are these centrally unique? Or?
The center is not unique. The center is not unique. In fact, actually, in our paper, we define the center manifold as just a pullback of this horizontal axis. But actually, there's nothing unique about the center manifold except the jet at the origin. So the first and second derivative of this curve is unique.
So it's a general PSC situation. Right?
It's a general Poisson situation. That's right. Yeah, that's right. Yes. Although when we actually employ it, we need to kind of formulate it in such a way that we can make it work for us. But yeah, but it's more or less just standard Poisson theory. Okay, any questions about this? Yes?
So I wonder if there's some special reason to put in the radiuses of this ball lambda power epsilon and not 1/2 power epsilon, because changing lambda to any other constant amounts just to multiply epsilon by something, but epsilon is arbitrary, so it seems that.
So So the reason why we did this, it's out of convenience. So basically, if you try to shrink it by some factor other than lambda to the epsilon, then you will have to make the corresponding change to L. Like the way L depends on epsilon will change if you try to do that.
I see. So this is just because the original definition of
that's
right.
Yeah. You can also think of it this way. Basically, I mean, 1/2 is just some arbitrary number. Of course, you can make it work if you choose epsilon super small. But the whole point of this thing is that the deterioration of regularity, this deterioration of the radius and so on, is small compared to the amount of contraction that we get in the stable direction. Right? So the amount of contraction that we get in the stable direction is lambda. So it's nice to be able to say relative to that, the loss of regularity is small. So that's why it makes sense. Let's do this. Okay. And then one thing that I have to say about this picture, and this is something which is different than Poisson theory, which is that in standard Poisson theory, you always consider the full orbit, both infinite forward and infinite backward. Because you're just talking about a typical point, and for a typical point, you have this picture in both directions, right? But it was important for us to actually break this time symmetry. So it was actually important for us to analyze what's happening in forward direction versus what's happening in backward direction, okay? So we will say that if you have this picture, but just for the forward orbit of P naught, then we would say that this thing is not Poisson regular, but forward regular with these quantization. Yeah? And if we have this picture just for the backward orbit of P naught, then we will say that it is backward regular, okay? Rather than Poisson regular. So let me write that down. Definition. If picture holds for for the forward orbit of P naught, so n greater than or equal to 0, then we say that P naught is L epsilon forward regular. And if picture holds for the backward orbit of P naught and less than or equal to 0, then we say that P naught is L epsilon backward regular. Okay. And let me introduce a notation. So we will say the set of all forward, backward, and Poisson L epsilon regular points will be denoted capital lambda. So it's a subset of the odometer. And we're talking about forward, backward, Poisson, regular points, and the quantities are given as subscripts. Okay, so L epsilon forward regular points will be this. If it was backward regular, it would be this, and so on. Yeah. So hopefully that makes sense. And what we can say is that remark. If a point is forward regular, like this, then actually, its stable manifold, S of P naught, has good geometry. And similarly, if P naught is backward regular, then its center manifold has good geometry.
But maybe on slow but exponentially shrinking boards.
Yes, true. So actually, you know what? I should be more specific. So let's label these balls as UIs. So U naught, U1, U minus 1, and so on. So then if you were to intersect this with U P naught, then it has good geometry. So that piece which you control by
For stable, there is no problem. For center.
For stable, there's no problem. Well, I mean, if you go far away, then who knows what it looks like. No? If you go far away, who knows what it looks like. But as long as you stay within this piece, then it will have some uniform bound on the C2 node. Okay. So just to say this in words while pointing at the picture, so if you just have this picture going in forward direction, then actually that suffices for you to conclude that this stable manifold, this piece of the stable manifold that's in this regular neighborhood, is what we call it, has, well, it looks like some pullback of a straight line under some uniformly bounded change of coordinates. Yeah? And if you just care about the center manifold, then all you care about is what's happening from the back. Okay, and now let me define unimodality, and then we can wrap up the part 1 of the mini course. So with unimodality, we define it in the following way. So let me say it like this. So in order to try and identify what unimodality should be in this context of two-dimensional maps, we knew that the derivative was not equal to 0 anywhere. So we had to kind of rethink what is the role of a critical point for dynamical systems, right? So the way we kind of interpreted it was a critical point for a dynamical system is an obstruction to linear behavior, is the way we kind of argued. And in the two-dimensional setting, this is what gives you linear behavior of the dynamics. Okay, so I mean, it can't be more kind of straightforwardly linear than this, right? So there's some control change of variables so that the dynamics actually just becomes a linear map, right? So a critical point should be something which obstructs this picture. And we define it to be, and something which would obstruct this picture is if the center manifold and the stable manifold were actually tangent to each other, right? Because here they're transverse, so it's possible to split them apart into horizontal direction and vertical direction, right? But if they were tangent to each other, then that would not be possible. So we define a regular critical point for these surface diffeomorphisms, a epsilon regular critical point of quadratic type. Critical orbit, actually, let's do that. Critical orbit of critical type is some orbit, infinite orbit, in your odometer, which satisfy the following 3 properties. First property is that, well, it has to have good stable manifold, so it has to be forward regular by this remark, right? So let's say that at the critical value, we have nice forward regularity. So we have this nice piece of the stable manifold. So let's say that the critical value is forward regular, like so. Second property is we also need a nice center manifold. So we'll assume that the critical point is nice backward regular. Actually, you know what? You can use L, some arbitrary L if you want. But for convenience, let's actually just assume that they're even nicer. Let's assume that the L is equal to 1. Smaller the value of L, the larger the size of the regular neighborhood where you have this geometric control, right? So let's assume that they're very nicely regular in forward and backward direction, if you look at it separately. But then here is the part which breaks Poisson regularity, which is that if you take the stable manifold of the critical value and you take the center manifold of the critical point and you see where they go under the map, it will go to two curves which have a quadratic tangency with each other. So we will impose that for this orbit to be a critical orbit of quadratic type, we need that the image of the center manifold of the critical point and the stable manifold of the critical value require that this thing has a quadratic tangency.
Can higher order tangency happen?
Higher order tangencies, well, what do you mean by can happen? I mean,
Not quadratic, but...
you mean within the Heron family or just?
Within Heron.
Oh, okay, so we don't know. I would guess, yeah, actually, I would guess that actually, yeah, arbitrarily high order
Quadratic, not
tangencies.
more. Yeah, or quadratic or better.
Sorry, what?
Quadratic or higher order or just quadratic?
Just quadratic. We require just quadratic. Just quadratic. But actually, like all the theory would still work as long as it was non-flat, as long as it has some finite order. Yeah, it would work. But in the Heron family, I think you can have any kind of tangency. Yeah.
So is this
Yes.
definition is required that the central manifold should be unique? Or is it not?
No. Oh, the only thing that you need is the jet, right? So you just need that at the points the curvature is unique.
Yeah.
Which it is. Yeah. So it's well defined. Okay. So let me just define unimodality and then I'll be finished. Okay. So if it's a regular critical point, then the critical value has. So let's say this is critical value, C3, and this is the critical backward image of the critical point, C3, and so on. Yeah. So if the critical value is forward regular, that means that we can draw this picture, but just going in the forward direction. Right? And it has this nice stable manifold like this. And since the critical point is backward regular, we can draw this picture going backward. So we have this nice center manifold like this, right? And the requirement, and these balls are, let me call them U1, U2, U3, and so on. U0, U -1. And the third requirement says that if you were to take the center manifold and you map it forward, then you obtain a quadratic tangency, like this. Okay. Okay. So this is the picture of a regular critical orbit, and we will say that definition, and then I'll finish. F is unimodal if. Okay. So we have this picture where there's this break in the traditional Poisson linearization, and we will require that as long as you avoid these backward regular neighborhoods of the critical point. So if you take a point in the odometer and you avoid the backward m equals to 0 to infinity, the union of the backward regular neighborhoods of the critical point, then all of these are forward regular. So that's the first condition, is if you avoid approaching the critical point too fast, then there's no problem with regularity in the forward direction. That's what it says. Second point is that if you take, if you avoid the forward regular neighborhood of the critical value, so infinity UN, and this is uniformly backward. Oh, actually, you know what? Let me change this a bit. I should add this quantifier to this theorem, to this definition. So there exists, so the critical orbit, so actually condition 0 is that there exists a unique epsilon regular critical orbit of quad type. And then once you have this, there exists some uniform constant L and some uniform constant delta, which is really small, but bigger than epsilon, such that this holds. So these conditions hold. Okay, and then we say that it is uniform. So the motivation for this definition is that basically, if it has this kind of critical orbit, where you have this tangency between the stable and center manifold, then it cannot possibly be uniformly Pessin regular, right? Because if it was uniformly Pessin regular, then at every point, the picture should look like this. There should be no tangency, yeah? So you're dealing with a non-uniformly partially hyperbolic system, and the unimodal system would be something where the lack of uniformity comes from exactly the presence of this critical orbit. Okay? So the only thing that obstructs forward regularity of your point is if it came into this regular neighborhood and then it did this thing where, well, this kind of nonlinear transition which takes horizontal line to something parabolic, right? And only thing that obstructs your backward orbit from being regular is if you came into this thing, right, where the straight vertical line becomes something parabolic like this. Okay, so this is what it means to be unimodal. And when you have a unimodal map, which is infinitely normalizable, then we'll be able to prove periodic bounds, like I've stated. Okay, I think I'm over time, so I should stop here. Thank you.
Since we are over time, let us postpone the questions to the break. And let us maybe